say I have a robotic vacuum cleaner like I do in my house, and it has a lidar scanner on the top, and that lidar scanner is bouncing off objects, and it's saying, 1 meter, half a meter, 6 centimeters. This is like the protocol semantics. There's no knowledge there about its overall surroundings, but it's this very low level notion of distance that keeps that robot from running into things. And that's adequate for it to navigate throughout the building without running into things, but doesn't know anything about its surroundings. So that's very similar to protocol semantics.
I'll do. Great. Well, Troy from Passive Logic, welcome to the podcast.
Yeah, thanks for having me here.
Absolutely. And today we're going to talk about the quantum standard, which it sounds absolutely fascinating. And when I read about it, I really wanted to get you on and discuss it in some more detail. So yeah, I thought maybe go on, sorry. I was saying...
No, happy to talk to you through quantum. Yeah.
A good place to start, it would probably be about Passive Logic. Do you want to give us a quick overview of what you guys do?
Yeah, so Passive Logic fundamentally is an autonomous things company, and we looked at what was happening in the evolution of the vehicles industry around making vehicles fully autonomous. And what we were really interested in is what we call ad hoc autonomy. How do you, by description, design an autonomous system that's a unique one-off for your own application, and from that description, be able to control it autonomously. So this notion is really important within the structure of buildings and industrial manufacturing, logistics, all these different use cases that are not coming off a conveyor belt of one after another of the exact same thing, but in each one of those applications, you have a unique, building. Every building's a little different, right? And so there's no one autonomous system that would do every building. You need to be able to have a user describe that building and then generate an autonomous platform for that specific use case. So this ad hoc autonomy is really the foundation of what we're working on here. And then quantum really fell out of that.
Great. Okay. So again, like quantum, do you want to give a overview, 360-degree view of what it is and how it came about?
So really what is quantum is it's a description language for autonomous systems. And it came about from this core need of, if we're going to build these autonomous systems around people's individual use cases for whatever their application is, somehow we need to describe that. And we developed this as a digital twin standard. Now, it's, I think, worthwhile to talk about digital twins broadly, because I think this word is being used in a lot of different ways throughout the industry. But I think when we look at how people think of digital twins, they usually have an in application in mind. What is their use case for a digital twin? And then you roll back to then what is that digital twin trying to accomplish, right? And so I think we can talk about quantum in those contexts relative to other digital twin standards.
Okay, great. I noticed on the website you mentioned that it's what you'd call a true ontology, right? Not just another semantic standard. So that really interested me. You may maybe sort of talk about what the difference there is.
I think this is a helpful frame of reference. So most ontologies aren't what I would call an ontology from the dictionary sense. They are what you would call a semantic standard. So what does that mean? So ontology is actually an existential word. It is a word developed by existential philosophers to say, what is my role in the universe? Why do I exist? And how do I, find my place, right? So what we're interested in technologically is, why does a pump exist? Why does a wall exist? Why does a control apparatus exist? And what is its job? Mm-hmm. This is a very different notion than semantics of what is that item's label? What is its name? And so what we would see in most digital twin standards is they're not much different than what you might think of if I took a BIM and put it in the cloud. Right. And so now you have to say, well, what are the use cases? There are use cases, but we believe those use cases are actually somewhat thin to just have them in the cloud. What we're interested in is, okay, if things know who they are and what they do, then they can all of a sudden make decisions, right? And you can't do that with just a labeling system. So maybe I'd break it down like this, from semantics to ontology. If I looked in the building space, the lowest level of semantic would be things like BACnet. These are what we call protocol semantics. These are the atoms or kernels of how do I tell a device, go do a thing. But they're very low level. It doesn't know what that thing is. And so what we're seeing in this gap is a bunch of semantic ontologies that are trying to organize the semantics of things so that that's not just a thing that I'm talking to over BACnet, whether it's 223P or whether it's haystack or whether it's brick. Oh, that's a light, right? I am telling a light to turn on. But that's not much more than a label, right? The labeling is giving it some language that's useful in English. I could have a label in Swedish, or I could have a label in German or Japanese, but those are still just labels. And so what's missing is purpose. Like, what is it fundamentally? What is it existentially? To know that it's a pump isn't very useful. To know what a pump is and how it works and what it does, now you can start making real decisions.
Mm-hmm. Okay, so that it has this sense of whatever this inanimate object might be, it has some sense of what it is and what it should do.
Yeah, let me contextualize that in something that's maybe tangible. Say I have a robotic vacuum cleaner like I do in my house, and it has a LiDAR scanner on the top, and that LiDAR scanner is bouncing off objects, and it's saying, 1 meter, half a meter, 6 centimeters. This is like the protocol semantics. There's no knowledge there about its overall surroundings, but it's this very low level notion of distance that keeps that robot from running into things. And that's adequate for it to navigate throughout the building without running into things, but doesn't know anything about its surroundings. So that's very similar to protocol semantics. If I put a camera on top and that camera had object recognition, and it'd say, oh, there's a door, there's a chair, there's a person, there's a filing cabinet. That's very similar to a brick or a haystack or 223 or real estate core. But it doesn't know what to do with that, right? Like, it doesn't know what a door is. It just knows that it is a door. But the ontological notion of what is a door is, well, a door is a router. What does it route between? It routes between two zones or two spaces. And the physics of that door is it swings on hinges. So I know if I open that door, one, it's going to swing open. I know how that's going to behave. And two, guaranteed there's going to be a space that I can navigate to on the other side. And that now all of a sudden becomes real actionable knowledge that the system can start controlling its own surroundings.
Okay, yeah, I mean, that's fascinating. And on, again, some of the things that I've read, you talk about describing the object's underlying physics, right? So that could be, again, maybe you could explain why that is also is useful.
Yeah, so when we think about autonomous things, and there's all these industries, and then in real estate, we have all these different categories of real estate. We say, okay, well, we need this existential layer. What is the meaning of all of this stuff? Well, you can try to find, meaning in a variety of ways. And we decided the most sort of underlying, what's the meta description of all these things, can be all boiled down to physics. And what we found was, and we can talk about the different aspects of quantum, but in quantum, we have what we call an actor model. And when we looked at all kinds of systems, we said, okay, here's IT systems, here is energy systems, water systems, and manufacturing. And as we looked around all these different kinds of systems, what we found is there's only 9 actors in any kind of system. And it doesn't matter what system that is. Let's say I have a store. A store in a heating system could be a tank of hot water. Mm-hmm. In an electrical storage system, it could be a battery storage for online, offline battery storage. And in a data system, that could be a flash drive, right? But all of those do the exact same role in no matter what system they're in. So the notion of actors is a key component to, who am I? And then how do I define the physics of the behaviors, which is another concept. If you are an actor, you have certain behaviors. Those behaviors must now be defined within your physics.
Okay, I mean, so is there some framework you're using to define this? Because so, for example, with like a semantic ontology uses RDF, right, to describe the relationships. So how are you using some kind of standard technique like that?
Yeah, so it's worth rolling back a bit. I'm a fan of RDF type approaches, but they also answer this specific semantic question, and this really emerged out of the 90s when the semantic web technologies were part of Tim Berners-Lee's view of the internet and where things would go. Right now, we have to think about AI in the 90s. What was AI in the 90s? It was knowledge-based systems, and they were these semantic systems. That was the state of the art in AI in the 90s. And it never found its footing. It's starting to find its footing in how do we describe protocol languages between one another, semantic labeling systems between one another. And that's helpful, but it also has its limits in that what it's trying to do is pure semantics. And we think that there's something deeper than that. So while we do express ourselves and can express ourselves in an RDF terminology, we see our quantum is first and foremost a graph language. Now that can be expressed in RDF, but what we're thinking more about is these not the semantic relationships, but these fundamental or physical relationships between things. And we want to express it in ways that developers can use it in a practical format. So for instance, while RDF is great, I only know hundreds of people in the world who even know how to use RDF technologies. So it's not practical for how are we going to get developers building stuff on top of this. So you need to give them object relationship methods. So we have an object model in multiple different languages. You need to give them practical APIs. So we have a GraphQL API that people can use to interface with it. So how do we give practical tools, not just research and R&D tools, and then fundamentally have a language, a graph language that can go from high level buildings, cityscape level graphs, all the way to compute graphs, which is what we're interested in, that you can run on a CPU or GPU. And again, that's not going to be an RDF type problem.
No, right. So because you talk about these 6 layers of data graph, right? So that's
right. Yeah. So you can think in quantum, you can think at different levels of abstraction. So the building level or the portfolio level abstraction, that's city level. Go down to the building level abstraction. Now I can navigate at the building scope, floors, zones, so forth. Go down to the system level. What are all the systems holistically within that building? Go down to the subsystem level. Once I get to the subsystem level, I can break that down to the equipment level. Equipment can be made of assemblies. That's another level abstraction within there. And then equipment is made up of components, and those components are made up of behaviors. And so it really depends on how deep you're going. At this top level, anybody can operate as a JavaScript developer in GraphQL without having to get deep into the ontology and be an ontology expert. But at the bottom level, we take quantum directly and stick it right into a GPU and process it as the AI itself. There is no other conversion to some other format. We are literally processing the quantum graph as the AI.
Wow, okay. And we mentioned some of these existing semantic standards, Project Haystack, Brick, Real Estate Core. How do you see quantum fitting into that kind of existing ecosystem?
Yeah, that's important. So I would think that it's crucial for all these different standards to operate together. Now, some of those have taken hold. Some of them may never take hold. So one of the things I look at first and foremost is, do they have a killer application? So Haystack had a killer application. That's why Haystack took hold. Whether some of the other standards take hold will depend a bit on whether they bring a killer application. But we're very dedicated to make sure that we're building connectors. So today we connect to Haystack. Today we import and export out of IFC. We import and export to energy modeling formats like Energy Plus, GBXML. But each one of those, if I look at Real Estate Core, it's maybe 25% of the quantum world, and Haystack is maybe 10% of the quantum world. Brick is maybe somewhere in between those two. What we're interested in, because of the nature of this autonomous systems problem, and we can get nerdy if you want and talk about heterogeneous neural nets and physics-based neural nets, but we need to describe it all, right? Yeah.
Okay. And quantum, is it open source? How can people get involved?
Yeah, so quantum, we're moving that out of Passive Logic as a technology in-house to its own alliance that will be open. We have now many different collaborators within the Quantum Alliance, everything from the real estate owner-operators to what is maybe the most interesting part of quantum, the manufacturers of equipment, because quantum's description of what things are turns out really valuable for makers of pumps and valves and air handlers and chiller plants, of how do we describe these at the point of manufacture so they can just plug and play within the ecosystem of a building.
Okay, and if a company wanted to get involved in the alliance, how would they?
Yeah, quantumalliance.org, and they can talk to the Quantum Alliance. We're happy to continue to bring in new players across the ecosystem of the building market, from owner-operators, controls manufacturers, makers of equipment, and that alliance has its own group, its own working group today, and is very happy to collaborate with other groups.
Yeah, I think this is fascinating, and I honestly see this as almost like a natural progression from where we're going, and whilst we have these semantic standards, and they're emerging now, but maybe in 5-10 years they're not going to be suitable, or we're going to need something more. And I think this is something like this comes in. Is that a fair reflection?
We'll have, I think there's this interplay between those that. Especially on the protocol standards. So in quantum, we have this notion of semantic lowering. So a little background on this. In compiler technologies, say you're programming in a high-level language like Rust or Swift or C++. In a higher-level language, you compile to an intermediate language, and then that typically is compiled to another intermediate language within another tool chain called LLVM. And then that's compiled down to the machine language. That's the atoms of how we communicate with the chips. This structuring from a monolithic approach to you just compile directly to the bottom, that was 30 years ago. What we've gone to is this layered approach of how do you lower from high-level context to lower-level context. So in quantum, it's very much the same thing. If you think about BACnet, or if you think about KNX, or you think about different protocol standards of how we communicate between devices, these are low-level semantics that we take the high-level semantic and we compile down to in real time, down to how do I say it. So I think of this as, whether it's BACnet or KNX or German or French or Swedish, the main concept here is, fundamentally, a table here is not a table. That's just a table in English, right? What is it doing? It's a gravity resistor. It keeps this from hitting the floor. That's its fundamental job. How we talk about it in different languages is not necessarily always translatable from language to language in a very direct way. If I say table and bureau, they mean slightly different things, right? But what is their fundamental job is to do the same role. And in this way, you can start this high-level abstraction. I want a pump to deliver 3 gallons a minute at 100 degrees Fahrenheit, that's in IP terms, or 40 liters a minute at 50 degrees Celsius, that's what you want, right? Now let me lower it down to, how do I say in BACnet, at this address, turn this device on to 65% capacity. That's the lower level context of what you actually want. And it turns out with new AI technologies, we can start with, what do we fundamentally want? And we can do what we call back propagate down to the language to actually get the communicatable piece to get the end result we want.
Oh, it's fascinating. And thank you for coming on and describing it. I think it's a really, really interesting subject. And I wish you luck with the Alliance. Is there anything else you think we've missed that you want to cover?
No, I think that's a pretty good intro to quantum and what we're doing. We have partners all the way on the compute side, from NVIDIA to the owner-operator side, like Brookfield. And so we're happy to collaborate across and collaborate with the semantic standards as well, as we think about where's the future of autonomy go, and then how do we connect to all of these different parts of the communication of devices, things, and networks.
Yeah, and we'll make sure we include a link to the website as well, so if people want more information, they can go
Great.
there. Thanks again, Troy. It's been a pleasure. Thank you.
Yeah, thank you.
Bye-bye.